Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Tiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series B.Arc Semester 1 Mathematics Lecture 2. In this lecture, we are going to discuss exponential function, De Moivre's theorem, summary. Exponential function. Exponential function is an algebraic function. It can be expanded as series also. This exponential function is denoted as e power x. This exponential function is applicable for all real values of x. Suppose this x value is complex, that exponential function is denoted as e power z, where z is the complex variable which is made up of the real part and imaginary part, or real component and imaginary component. Real component can be u, imaginary component can be y. So, combination of this real component and imaginary component is represented as u plus iv. So, z is equal to u plus iv is the form of complex function. If that complex function is exponented, then it is denoted as e power z. So, exponential function can be given for any real function as well as for complex function. In series form, this exponential function of real value x is expanded like this, that is e power x is equal to 1 plus x by 1 factorial. Actually, this x is nothing but x by 1 factorial. Since 1 factorial is equal to 1, x alone is taken. So, 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc., and it goes till infinity. So, this is the series expansion of real x as exponential function. Then this exponential function can be used in any of the expansion. Here in this problem, we are asked to find the coefficient of x power n in the expansion of a plus bx. Earlier in the definition, we have seen the series expansion of x alone. In this problem, instead of ax, a plus bx exists. So, how this problem can be solved is, let us take e power a separately and e power bx separately, because this e power a plus bx can be bifurcated, can be splitted as e power a into e power bx. This a is a constant, no variable exists. So, e power a will exist as it is. Then x is a variable. So, that x is b times. So, that e power bx, that e power bx can be expanded using this series expansion. Then that e power a can be multiplied. Then we will get the coefficient of x power n in the expansion of this e power a plus bx. So, solution to this problem can be obtained like this. First expand this e power a plus bx. So, I told you this e power a plus bx can be written as two component as e power a into e power bx. This e power a is a constant, so we can keep this e power a as it is. Then this e power bx can be expanded using the series expansion of e power x. So, 1 plus x by 1 factorial. Instead of x, bx exists. Then x square by 2 factorial. Instead of x, bx the whole square by 2 factorial plus etc. Then n term bx to the power n by n factorial plus etc. and it goes till infinite. Here in the problem we are asked to find only the coefficient of x power n. So, x power n exists only in this area. So, let us take that component alone. So, coefficient of x power n is equal to e power a into bn by n factorial. This is the coefficient of x power n in this problem. So, from this example we learnt how to apply the series form of exponential function or series expansion of exponential function. Then complex form of exponential function. Complex form of exponential function. I told you z is a complex function. This z can be expressed as either u plus iv or z is equal to x plus iy. Either way you can express a complex function. Here in this situation we will take this form z as x plus iy. I told you that z complex function can be exponented. So, instead of this z, substitute this x plus iy. So, x plus iy. This is similar to the form explained in the previous problem. In the previous problem, e power a plus bx. Instead of bx, here we got iy, a complex variable. Instead of a, x. So, this can be represented as two functions as e power x into e power iy, e power x into e power iy. We know this e power x can be expanded as 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus etc. It goes till infinite and e power iy. Like this, if you expand this e power iy, you will get 1 plus iy by 1 factorial, a complex one, then iy the whole square by 2 factorial, like that it will keep on go. So, it is a multiplication of two infinite series. To leave this e power iy exponential of a complex function can be represented using a trigonometric function, that is e power x into cos y plus I sin y. This is how imaginary part of a complex function can be represented trigonometrically. This is how e power z can be expressed. So, e power z is equal to e power x into cos y plus I sin y. Then this e power z is also a periodic function. E power z is also a periodic function with periodicity 2 pi I. Periodicity of e power z is equal to 2 pi I. So, equationally you can represent this periodicity as e power z plus 2 pi I is equal to e power z. If it goes n number of times, e power z plus 2n pi I is equal to e power z. This is how periodicity of this complex exponential function can be written. Then some standard result in this exponential function. What are the standard result in this exponential function is we learned that e power x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus etc. plus infinity, till that it will go. Like this you can expand exponentially the negative of a real function. So, e power minus x. This e power minus x can be defined or represented as 1 minus x by 1 factorial and plus x square by 2 factorial minus x cube by 3 factorial plus etc., and it also goes till infinite. So, like this negative of a function can also be exponented. That explanation will give an exponential function similar to this. An average of these two can be taken, that is e power x plus e power minus x by 2. That is also an important result in the exponential function, series expansion of exponential function. Average of these two functions, e power x plus e power minus x by 2 is equal to 1 plus x square by 2 factorial plus x power 4 by 4 factorial plus etc., and goes till infinite. So, average of that two function will come like this. Here you can see only the even powers of x. Then e power x minus e power minus x by 2 gives a result like this: x plus x cube by 3 factorial plus x power 5 by 5 factorial plus etc. till infinite it will give. Then if you substitute 1 instead of x, we know the expansion of e power x. If you substitute 1, e power 1 is nothing but e. So, e is equal to 1 plus 1 by 1 factorial. Instead of x, 1 is substituted here. Then 1 square, again 1 by 2 factorial plus 1 by 3 factorial, like that it goes till infinite. So, this is the value of e. Then e power minus 1, e power minus 1 is equal to 1 minus 1 by 1 factorial, then plus 1 by 2 factorial, then minus 1 by 3 factorial plus etc. till infinite it goes. So, this e power minus 1 consists of both even term and odd term. Then average of these two, that is e and e power minus 1 gives what? E plus e power minus 1 by 2. Average of that two gives 1 plus 1 by 2 factorial plus 1 by 4 factorial plus it goes till infinite. Average of that also gives this one. So, this is how some of the important results in the series expansion of exponential function can be learnt. Next, de Morbius theorem. Here in de Morbius theorem, if n is an integer whether positive or negative, if n is an integer either positive or negative, cos theta plus I sin theta the whole power n is defined like this: cos theta, cos n theta plus I sin n theta. This is the de Morbius theorem. And if n is a fraction, positive or negative, then this cos n theta plus I sin n theta is one of the value of cos n theta plus I sin theta power n, cos theta plus I sin theta power n. This expansion gives many values. Out of those values, if n is a fraction, positive or negative, then this cos n theta plus I sin n theta is one of the value. This is the de Moivre's theorem. Proof of this de Moivre's theorem can be explained like this. Proof of this de Moivre's theorem. Here this proof can be explained in 3 cases. Case 1. In the first case, n is taken as a positive integer. N is taken as positive. So, we got cos alpha plus I sin alpha into cos beta plus I sin beta. If n is taken as positive, we got this one. Then expansion of multiplication of these two gives cos alpha into cos beta minus sin alpha into sin beta plus I into sin alpha cos beta plus cos alpha into sin beta. Here the real part and imaginary part are separated after the multiplication. Cos alpha plus I sin alpha into cos beta plus I sin beta is multiplied, then real part and imaginary part are separated, we got the thing. Then further simplification of this, after applying some trigonometric formula, we got cos alpha plus beta. So, cos alpha plus beta is equal to cos alpha cos beta minus sin alpha sin beta plus I into sin alpha plus beta. So, sin alpha plus beta is equal to sin alpha cos beta plus cos alpha sin beta. Now, similarly multiplying by cos gamma plus I sin gamma on both sides. Multiplying by cos gamma plus I sin gamma. I sin gamma, we get cos alpha plus I sin alpha into cos beta plus I sin beta into cos gamma plus I sin gamma. Here we are multiplying both sides by cos gamma plus I sin gamma, which gives cos alpha plus beta plus gamma plus I sin alpha plus beta plus gamma. So, this is how we get. Proceeding in this way and continuing up to n factors, we got cos alpha plus I sin alpha into cos beta plus I sin beta into cos gamma plus I sin gamma into 2n factors. So, after that you can use cos u plus I sin u, then cos v plus I sin v, like that. If we keep on go till n factors, we get cos of alpha plus beta plus gamma plus n terms plus I sin alpha plus beta plus gamma plus etc. till n terms. So, this is how we will get after simplification of this we got this. Now, if this alpha, beta, gamma everything is equal to gamma etc. is equal to theta, then the above case will become cos theta plus I sin theta to the power n. That means this is multiplied n times is equal to cos n theta plus I sin n theta. So, this is how de Moivre's theorem can be proved for the case if n is taken positive. Similarly, the same theorem can be proved for the negative integer. If n is equal to a negative integer minus m, then this can be again proved as cos theta plus I sin theta to the power n, which is equal to cos theta plus I sin theta to the power minus m. Here we have equated, we took that minus m, n is equal to minus m, that is substituted. Then it can be further written as 1 by cos theta plus I sin theta to the power m, then which is equal to 1 by cos m theta after applying de Moivre's theorem in this case, cos m theta plus I sin m theta, cos m theta plus I sin m theta. So, further manipulation of this gives cos m theta minus I sin m theta over cos m theta plus I sin m theta into cos m theta minus I sin m theta. So, further to simplify this further, this is how it proceeds. Then we got the value as cos m theta minus I sin m theta, which is equal to cos of minus m theta plus I sin minus of m theta, because we know in trigonometry cos of minus theta is equal to cos theta, then sin of minus theta is equal to minus sin theta. So, instead of this minus sin theta, sin of minus theta is taken. So, we got the thing, this minus m is nothing but n. So, substitute the value cos n theta plus I sin n theta. So, this is how de Moivre's theorem can be proved for negative integers, n is equal to negative. Similarly, we can prove for n is a fraction, if n is a fraction. Suppose n is equal to p by q, then de Moivre's theorem can be proved like this. We got final thing as cos p theta by q plus I sin p theta by q is one of the value of this cos theta plus I sin theta to the power p by q. So, this is one of the value of this cos theta plus I sin theta p by q. Here that p by q is a fraction. So, we got this cos theta plus I sin theta power n as n is equal to p by q is equal to n. So, here we can prove that de Moivre's theorem is applicable for fraction also. If n is fraction, de Moivre's theorem can be applied. This is how de Moivre's theorem can be proved. So, using de Moivre's theorem, you can prove the following example, that is 1 plus cos phi plus I sin phi over 1 plus cos phi minus I sin phi is equal to cos n phi plus I sin n phi. Using de Moivre's theorem, prove this example. Now apply de Moivre's theorem. So here to the power n in this problem, to the power n. So let us take the left hand side of the problem. So if you take the left hand side of this problem, substitute some of the trigonometric formula. So this expression will change as 2 cos square pi by 2 plus 2I sin pi by 2 cos pi by 2, cos pi by 2 over 2 cos square pi by 2 minus 2I sin pi by 2 cos pi by 2. So this is how the left hand side of this equation can be simplified to half angle after substituting some of the trigonometric formula. Now substitute further simplification of this gives cos pi by 2 plus I sin pi by 2 over cos pi by 2 minus I sin pi by 2 to the power n. So this is how the above expression can be further simplified. Now substitute the de Moivre's theorem. So cos pi by 2 plus I sin pi by 2 the whole square. So this can be further simplified like this, and the power n exists as it is. Now apply the de Moivre's theorem for both the power. So we will get cos n pi plus I sin n pi. So to obtain the solution, this de Moivre's theorem is applied for 2 as well as for n. First, if we apply de Moivre's theorem for this 2, it will become cos 2 phi by 2, 2 get cancelled. So cos phi plus I sin 2 phi by 2, again 2 gets cancelled, you got only 5. Then that is raised to the power n. Again substitute the de Moivre's theorem, we got cos n phi plus I sin n phi. So like this 1 plus cos phi plus I sin phi by 1 plus cos phi minus I sin phi to the power n is equal to cos n phi plus I sin n phi can be proved. So this is one of the application of de Moivre's theorem. Like this, de Moivre's theorem has got many applications in trigonometric function and exponential function. In this lecture, we learnt the thing about exponential function or algebraic function. Exponential function can be expanded as a series. E power x is equal to 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus etc. plus infinity. So like this, exponential function can be expanded as a series. Then the same exponential function can also be applied for complex variable like e power z. E power z is equal to e power x plus iy. So that can be simplified as e power x into cos y plus I sin y. Then we learnt de Moivre's theorem. This de Moivre's theorem gives the power of the complex exponential function like e power I theta or e power cos theta plus I sin theta to the power n can be written as cos n theta plus I sin n theta. This is how de Moivre's theorem is defined and applied in the exponential function. These are all the concepts we learnt from this lecture. After listening to this lecture, you can answer the following questions. Define exponential function, state de Moivre's theorem, then expand e power I to x. These questions can be answered after listening to this lecture. Thank you.